Okay, today we have the integral from 0 to pi on 2 of x cotx. There's going to be a few steps to this integral, and the first step is by parts. So we have the thing to differentiate as x, and differentiating that thing will give us 1. The thing to integrate we'll have as cotx, which if we write it as cos over sine, we can see when we integrate that thing, we're going to get the natural log of sine. Sticking that together then, our integral is going to become u times x, so x natural log of sine x, evaluated at pi on 2 and 0, minus the integral of u dash v, so 1 times the natural log of sine. And that's evaluated, again, between 0 and half a pi. So this integral now we'll call j, and it's going to be our focus for part 2. So the second step of our integral is to notice that sine and cosine occupy all the same values in our region between 0 and half a pi. So that means that when we integrate any function of sine and cos, they're the same. So this integral we have at the top, we could also write it with cos in there. So it's also the integral of half a pi and 0, natural log of cos of x dx. This is useful because now we can add the two together. So we can say 2 times j is equal to the integral from 0 to pi on 2 of the natural log of sine plus the natural log of cos. Now use the log laws to combine this stuff. So we'll have the integral, again 0 to pi on 2 of the log of sine times cos, which if we use the double angle formula, this is going to give us the integral, again same limits, pi on 2 and 0, of the log of half of sine 2x. Using log laws again, we can separate this out into the integral pi on 2 and 0 of log of sine 2x, subtract log 2, all integrated. And that log 2 then is just a constant. We can perform that integral nice and easy and get that this whole thing is integral pi on 2 and 0 log of sine 2x take away pi on 2 times log 2. And now then, part 3 is going to be focusing on this integral in here, which we'll call k. So to attack this, we'll use a u sub, and we'll have u is equal to 2x. So du is equal to 2 dx. So our integral then, we can transform that now into a half. Our limits are all going to double, so we've got pi and 0 of just sine x, or sine u, I suppose. The next thing to notice now, very similar to the step before, is if we look at sine in the range from 0 to pi, it again occupies all the same values as it did before when we split it at pi on 2. So this integral is twice the integral from 0 to pi on 2. So if we half that, we have just the integral from 0 to pi on 2 of sine, and we'll change the u to an x. That's completely fine. This thing then is equal to the j that we had up here. So altogether we've worked out that k is equal to j. And now if we go over and take this identity that we've got on the right, that 2j is equal to k minus pi on 2 log 2. So 2j is equal to k minus pi on 2 log 2. If we know that j is equal to k, what we can say then, this is j is equal to minus pi on 2 times the natural log of 2. This leads us nicely on then to the next part, which is to figure out what does this original bit equal. So part 4, we'll plug in pi on 2, and we'll get sine of pi on 2, which is 1. Natural log of 1 is 0. 0 times x is 0. Nice and simple. When we plug in 0 though, we're going to have sine of 0, which is 0, and the natural log of 0 is undefined. So we need to think about this as being the limit, and we'll have negative because it's the pi on 2 take away the 0, like when we plug those numbers in. As x goes to 0 from the positive side of x, log of sine of x. We can rewrite this then as the limit, again, as x goes to 0 from the positive side, still with the minus at the front, of the log of sine of x over x to the power minus 1. Completely fine, nothing's changed there. And now if we use L'Hopital's rule and differentiate this, we can see that it's equal to, again we have the negative, limit x goes to 0 from the positive side of the differential of the natural log of sine, which is cos on sine, multiplied by the differential, or 1 on the differential, of x to the power minus 1. So minus x to the minus 2. These minuses cancel off, and we can actually bring our x to the minus 2 to the top. So what we've got now, again the limit as x goes to 0 from the positive side of x squared cos x over sine x. This we can separate out into a product. We'll have the limit, again x goes to 0 from the positive side, of x over sine x multiplied by x cos x. This thing then is a product, so we'll take it up to this left hand side and we can write it as a product of limits instead of a limit of a product. And we'll actually use the power laws as well. So again we've got the limit as x goes to 0 from the positive side of, if we flip this fraction and have sine x over x, we can say that this is to the power of minus 1. Using the power law of limits, we can bring the minus 1 out of the side. We've also got then the limit as x cos x goes to 0. Well, cos x of 0, well, cos of 0 is 0. 0 is 0, so this whole thing ends up being 0. Now then, we can write our sine of x using the Taylor series. So again, we'll have the limit as x goes to 0, and we'll have 1 on x, but if we think about immediately dividing by the powers, we're going to have 1 minus x squared on 3 factorial plus x to the 4 on 5 factorial, etc, etc, etc. And this then, when we plug in 0, all of these terms involving an x are going to go to 0. So all we're left with is 1. So this entire limit ends up being 0 times 1, which is 0. So now then, if we go and look at our original integral, what we've shown is this whole thing is equal to 0, and this whole thing on the right is equal to pi on 2 times the natural log of 2. So that is our final answer.